All right, everyone. Thank you very much for coming to our webinar for September, which is going to be on multivariate analysis of process data. I see a few new faces or names and some regular attendees, so thank you for keep coming back. I am going to do just kind of a quick overview about the history of multivariate data analysis in general before we get started, and then we're going to do a quick example using some process data, and then I'll kind of do a summary and explain what your process of building models might be in general, and that applies to both process and non-process data. So originally, well back into the day, the scientific approach usually looked at one specific variable at a time. These are univariate methods. So if you ran an experiment, you would hold everything the same except for one variable and change that one, and then you'd run another experiment where you'd hold all of the variables and change a different variable. And you did that mainly because there were only a few measurements available, and in spectroscopically speaking, there was very limited resolution. But in about 1975, that's when we came up with some multivariate methods and chemometrics. And the reason why is that by this point we had some cheap measurements. So you could take lots of different measurements. The experiments themselves became expensive, so you had to be very careful about what types of experiments you did. And then we had adequate computers and methodology to interpret that data. So why multivariate again? So in the real world, most processes are multivariate. So we have multivariate problems like the weather, for example. So what types of variables go into account for how you predict the weather? You've got lots of factors. You've got wind, air pressure, temperature, dew point, your season, etc. Right? And all of these things are correlated with each other. If you just measured the wind, it wouldn't tell you if it was a rainy day, for example. So you need to do lots of different types of measurements to get the full picture. And there's lots of different sensors for these particular factors. So we've got an anemometer, barometer, thermometer, hygrometer, calendar, to take all these things. So using the output from these sensors, we can determine what the weather is. So when we're talking about process data, if anyone's worked in any sort of manufacturing, you've seen something like this, these control charts. And now this is just two, for example, but you might have 10, 15 different control charts that you're monitoring at the same time. Now, what you can see here is we've got a temperature control chart and a pH control chart. And looking at these, you'd see there's nothing that's out of control. The temperature is remaining within the regions that we expect. Nothing's extreme. Everything's hunky-dory. Same thing in your pH control chart. Now, here's the problem. In this particular situation, the temperature and the pH are related to each other. There's a cross-correlation. So if we plot temperature and pH against each other, we get a view like this. This is our multivariate view. And you can see immediately that you've got one particular data point here that is very different from the rest of the data points when you look at this full picture. And using our univariate limits, you see that there's still no warning in that case. So what we do is we apply multivariate limits. So this is this design space that we say is acceptable for our control chart. So a multivariate control chart would look more like this, and then you would have a highlight for this particular example that's well out of spec compared to the rest of it. So when might we need to use multivariate data analysis to do this? So in that case, you just plot two things versus each other, no problem. So what if you have an example where you need to measure the temperature in a furnace load? It's pretty improbable or impossible to directly measure this you can't really stick a thermometer in there. It'd be a very expensive thermometer, I think, that could handle those kinds of levels of heat. So what we do instead is you actually do an indirect measurement with an IR emission spectrometer. And you need a multivariate data analysis approach to interpret these more complicated measurements, these indirect measurements. So we also do some softer empirical modeling. We like to observe processes with all of our available information and measurement techniques. And some of these processes, they follow the laws of physics or other theoretical models and can be modeled from first principles. And you can start reducing the number of variables, reducing the number of things you need to watch in order to know what's going on. And then you've also got processes that are very complex in nature, and the empirical data can form the basis for that analysis. So multivariate methods are required to analyze the data. This makes use of that background knowledge in your theory. It ensures that you have a correct interpretation and a most comprehensive validation. So it makes sure that you have the full picture before you move forward, so you can stay in real control. Now, when we go into data analysis and practice, we need to keep in mind that a significant portion of your data analysis comes from you. You are the expert on your particular application. So we say about 75 or 70% of the data analysis, it comes from your application knowledge and your common sense about your data. You know your data and your process more than any program might do. So the rest is statistics and mathematics. And what the unscrambler does is it gives you a tool to easily apply your statistics and your mathematics so you can focus on the rest of the analysis. Okay, so let's look at an example. I have here some data that is from a paper mill. And one of the major quality measurements that is important for this paper mill is print through. So, of course, when you buy paper, if you print on one side, you want it not to bleed through to either the next page or sometimes even the back of that same page. So it's an important quality to know how good your paper is. So you can see we have a lot of different variables in here that we can look at. We've got the weight of the paper, ink, that's going to be how much ink they put on the paper. That's what's going to be measured for the print through, is how much ink they put on it. We've got brightness, how well it scatters, light scattering coefficient, your opacity of your paper, etc. So there's a lot of different variables that are being measured. And what they want to do is be able to predict this print through based on some of these variables. And you want to narrow down as many variables as possible because maybe one or two or a couple of these are very difficult to measure, or they are expensive to measure, they take a long time. So you want to get as parsimonious a model as possible. So one of the first things I do when we look at this is we're going to take a look at your descriptive statistics. Under Stats, Analyze Descriptive Statistics, and I'm going to do my process variables. And what this shows us is your box plots of your data. And what you can see right away, so one box plot, that's going to show your median is the center line. Each quartile, so from the 25% to the 75% quartile, is in the box. And then these are your min and maximum points. Now what you can tell from this is that all of these variables have very different output ranges, standard deviations, and even nominal values, right? Ink down here is very, very low compared to, say, your density. Now, if we did an analysis directly on this data, what would happen is we would see that permeability and density would be a very significant variable by default just because they have very high numbers compared to some of these other things. So what this tells me is that I'm going to have to do some sort of pre-processing. In this case, we probably do a mean center and scaling of the data. And what that does, so mean centering will divide all of these by their individual means so that the mean value will be on 0. And then what you do is you can scale by the standard deviation so that they're on the same variability scale, roughly. And I'll show you how you can do that. There's a couple ways, but I like to take a look at it first. So we're going to do a tasks transform, and we have down here center and scale. Process, we'll do all. Now you can see there's a number of different ways you can center. I tend to do mean centering. There's specific times when you might use your median or minimum, but we're going to go with mean. And we're going to do your standard deviation. We pick OK. And now if we do our descriptive statistics again, quality, process, training, now you see that the mean centers around 0, and the variability is on a relatively even scale. So that one, if you had one that doesn't move very much, it's not labeled as not contributing very much, for example. Okay? So let's run a PLS model on this. We're going to do tasks, analyze, partial least squared. And notice I'm doing this on the raw data. I'll show you the other way to apply some weights to your data. Process. Now we have split this into some training and test sets. That's very important for validation of your models. So once you build your model and you feel pretty confident in it, you need to run a test set of known values to make sure that it predicts the way you expect. And what we want to predict is our quality. That's going to be our print through. We need to go to this X weights. Now this is where you can apply some weighting. We have lots of different types of weighting that you can do. The general one that I'm going to do here is this mean divided by the standard deviation. And you need to go up here, click all, and then make sure to hit update. And you'll see that under here, under the weight, it shows that each individual variable is weighted. Now, if you ever are working with this type of data plus spectroscopic data on top of each other, you might weight things differently, and you can do that individually if you want to. So we could bring this back to a constant, for example. We're also going to weight the y's just to be thorough. And every time we do anything in the unscrambler, we always validate. Validation is key. This is the way that you can show how likely you are to predict accurate results in the future. Okay, so under here we're going to do setup. There's lots of different ways you can cross-validate. In this case we're going to do random, so it's going to take out a random selection of your samples and pull those out. It'll run your PLS regression using the rest of the samples, and it will predict these samples back in on that. And it repeats that multiple times until every single data point has been pulled out once. Now I'm going to go with 10 random segments. What that's going to do is say that 10% of our data is going to be pulled out, and we're going to build the model based on the other 90% and predict them back in. If we did 20 samples, you'd only pull out 5% of your data. And you sort of determine the number of segments you want depending on how large your data set is, how influential you expect your individual data points to be. And here's our first model. Now the first thing we want to look at always is our explained variance. And we can see this is our explained variance for y. And you can see most of the information is captured in one factor. We're looking at about 81% of the variability in y is explained here. And the second variable brings us up to 87%, and then it levels off. So what that tells me is I absolutely don't want to use any more than 2 factors. If we start getting into 3 factors, 4 factors, we're not gaining any extra information, and you might wind up with over modeling and predicting some noise, and then your predictions actually might not turn out very well if you get a random strange reading at some point later in the future. So the next thing I look at is my scores, and we're going to put our hoteling t-squared ellipse on here. Now this is basically like your standard deviation around the model to show this one has a 95% confidence interval. In a typical case, you would expect 95% of your data points to lie within this ellipse and about 5% on the out. So we have a couple who are out here, but they don't seem very extreme. So I'm not worried about them at this particular point. We also want to look at our X and Y loadings. I'm going to show labels. And now we can interpret what the model looks like. So what we're predicting is here in red, the print through. And so what we see is that the print through actually lies very close and far along on principal component 1. So really, principal component 1 explains a good portion of the print through. Remember we said 81%, which is pretty good for a first principal component. Now, what you can see here is in factor 1, it's actually telling us that only 18% of the variation in the X data is being used to describe that 81% of the print through. So what that tells us is that we likely can remove some of these variables. So we don't have to measure or study every single one of the variables to get an accurate prediction. In factor 2, on the side here, we see that 16% of the variation in X describes another 6% of the variation in Y. Now, one thing we can do if we go back to this explain variance, if we right-click and look at variances, we're to do X or Y. And this is showing everything, but we can go and look at each individual variable to see what is being described. So you can see here that filler isn't described very well by factor 1 and factor 2, but in the later ones it starts to be explained a little bit more. You can see the total on here as well, so you can see how that's, if it's doing better or worse than the overall X variability. And if we go through here, you can just take a look. You can see this, imagine, doesn't predict very well. It doesn't explain very much about your waste paper, and so on. Thermopulp, if you get into about factor 4, it starts really showing up. But then the question is that really important to this analysis? If we keep going through, we can see here at factor 3, the ground wood comes in. But remember, we don't really care past factor 2. If we start getting into factor 3, factor 4, we're not actually getting very much extra information about Y, which is what we really care about in this particular case. We'll just kind of go through here. So you can see here we've got this PPS, which is a print surface number. That's something proprietary to this particular paper mill. We can see density has a pretty good understanding here. That would make sense, right? The denser the paper, the less likely the print's going to go through. The permeability of the paper, that starts to explain. The roughness, how rough it is, affects how well the print goes through. And this is a huge one, the opacity. And this makes sense. And you always want to do a gut check, especially with these kinds of process variables. It makes sense that if you look at a paper, if you can see through it, then ink is likely going to go through it as well. So there's that. And we can look at this. We've got this. Now remember I said that that we shouldn't use any more than 2, right? So the unscrambler actually by default wants us to use 3. It's only looking at this RMSEE, that's how accurately it's predicting, and the overall how much it's explaining, right, of your variance. So what I'm going to do is, if we've decided, like we have, that we don't want to use more than 2 variables, we're going to move this back. All right, so it's not quite as tight, but it's still okay. Now this graph shows what we predicted versus what our reference was. And we can show our regression lines, and the blue is the calibration. So that's using all of the data set and repredicting them back in on themselves. And the red is your cross-validation. And if your cross-validation is very close to your calibration, that shows that you have a pretty good calibration. You don't have any crazy outliers typically. Okay, now the RMSEE. What you need to keep in mind here is that these numbers are in the same units as your original data points, right? So your print through, this is how accurate it is on this print through. So if we're looking at around 52 is a general print through in the center here, we are off by, say, 3.4. So we say that if we're predicting at 52, it could be anywhere in this kind of range, plus or minus 3.4. Okay, now is that good? It depends on your particular situation. You have to know how accurate you need your product to be, right? So in this case, that 3.4 in the center of your data, 3.4 divided by, say, 52, so that's about a 6.5% error. Now, a lot of places, if you're looking at paper, that's probably accurate enough. If you're doing something with humans, which wouldn't be that case here, but if you're predicting what people might like, for example, that would be amazingly accurate. If you're looking in the pharmaceutical world or really high-tech technology, building computers, for example, then maybe you need a narrower margin. So that's really up to you, your application, what you need it to be. And remember, this error is only as good as your reference data. If my reference data varies by 5, then this is saying that my model it's a better predictor, but it can't actually predict better than the original data because there's so much variation in that. So basically you're limited by your original measurement. Now, if your original measurement here for print through was 0.03, then that's saying this is much more, has a higher variation than that. So you just have to weigh those two. But in general, the closer this error is to 0, the better. You want lower numbers, right? You also want to look at your R-squared. That's how well the data fits the line. Depending on your process, over 80-85% is pretty good. Some places you need 95-99%. Again, it depends on your particular application. So let's take a look at these loadings again. And we have this thing called the correlation loadings. This helps us determine which variables are important. So we can see that in principal component 1, that's going to be in this direction. What these ellipses are is this is 50% is being explained, 50% or more, to 100%. And so anything that is between those two ellipses is important for these particular principal components, these particular factors. So in this case, factor 1 is mostly your opacity, your scatter, a little bit of your weight, right? And principal component 2 might be your roughness and the density, and everything in the middle here really doesn't factor in. Now you can see I have a number of variables here that are automatically selected, and I'm going to show you what those are. So if we right-click and say PLS, we're going to look at important variables. What this does is it shows how that particular variable, the strength of that component, and how much it varies, right? So if you have a high strength and the variation stays on one side of 0, then it's considered an important variable. You can see here that permeability, it crosses 0 a little bit. So if you have a particular variable that sometimes as it's increasing, the output is increasing and sometimes it's decreasing when the output's increasing, then you have a variable that doesn't really tell you much about it, especially these, right? Your oil absorbance, your ground wood, those are absolutely clearly not important variables. So you know that you don't have to look at those anymore. I'm going to go back to your overview. Another thing we want to look at is to see if we have any outliers. We do have a couple that are lying out here, but we don't want to make a decision on this just from the scores plot. What we want to do is go to these residuals and influence, and this gives us our hoteling t-squared. So again, that's the hoteling t-squared is the distance an individual point is away from the center of the model. And your Q residuals is how similar I tend to think in spectra, so how similar the responses are compared to the rest of the data. So if the spectrum looks the same, then it's going to be down in this quadrant. Now you have these nice lines to help you determine when you have outliers. If you have something that has both a high residual and a high hoteling t-squared, like this particular one, then that's most likely an outlier. There's something different about that particular sample that means that it's not like the others. So you might want to throw that particular sample out. So when I highlight it here, what we can do is go back at your regression overview and see where it falls. It's right in the middle. It doesn't look like it maybe has a high influence, but we have statistical reasons to remove that particular data point. Let's take a look if we can sample group in our scores. If I right-click sample grouping, what we can do is make a color coding based on the quality. We choose this, say create row sets, and this is going to evenly distribute the ranges from low range to medium to high. And what we see low, medium, high, kind of goes a little bit diagonally through here. We've got a couple out here that seem a little extreme. And so those I might click on, see where they fall in here, how they fit on the lines. They're pretty far off from where you would expect them to be predicted, as is this particular one. Another way you can spot outliers is when here you can see that the calibration and the validation sample are kind of spread apart from each other, especially if it's significantly more than that. If, say, the calibration one was right on the line and the validation's way up here, then there's something going on with that particular sample that you might want to remove them. So I'm going to go back and look at my residuals and influence again. And we can see that the ones that I highlighted are kind of extreme samples. And I would say if we're going to remove those, we might want to remove this one as well. Now, how do I recalculate that without those particular samples, right? In the unscrambler, it's very easy. You right-click, recalculate without marked samples. We're going to keep everything else the same for now. Oh, I have a question that says if we use 3 factors, we will have a smaller RMSE. Shouldn't we go with 3 factors? So that is a good question, and we get that a lot. So the problem with going with that is let me go back to here. What you see with your explained variance, right, is when we get to factor 3, we're only increasing about 1% of explained variance. Also, the RMSE doesn't change that much. The 3 goes from 3.2 to 3.4. You risk over-modeling at that point. So the RMSE is only one of the things that you want to balance when you are determining how many factors to use. Let me make this plot a little differently. Right, so we're going to do our root mean squared error. What we tend to say, this is what we call a press plot. This is how much, that root mean square. So what you see generally is a big drop off, and then eventually it kind of plateaus. Now, when you get to this point, if it starts to plateau, you don't gain anything significant by going to that third factor. Yes, you get a lower RMSE, but it's so minimal that it's not worth going to that point because you risk over-modeling it. Oh, why did I build the model with the raw data, not the mean centered? So I actually did do the mean centering. I just did it when I built the model. Let me show you that again real quick. Tasks, Analyze, PLS. This weights, process, quality. This weighting is the same thing. This is mean centering and scaling right here. I'm just doing it here instead of in the beginning. You could do it either way, but this way is a little bit more straightforward. I was just showing you what it would look like after you've done the center and scaling. Okay, I hope I clarified those things for you. All right, so now we have a new one. And what we see here is that we've actually improved our predicted versus reference, our RMSE. We are explaining a little bit more in our 2 factors. We're up to 89%, so we got 2% more. And so we're not seeing very many, we shouldn't really see any outliers at this point. But if you do, you can still keep kind of going through and picking through it. Let's look at these. All right, everything goes the way you would expect. These are still lining up pretty well. Okay, except now that factor 2 doesn't really influence as much as it did previously. Now, what we want to do, again, we want to go with the most parsimonious model, the simplest model that explains our print through as well as possible. So we know that most of these in the middle here don't affect our quality. Oh, I've got right? So I have the particular ones that are automatically selected. We're going to go with those for now. I might actually include roughness, so I'm going to click that one as well. And what we can do is go back to this PLS, right-click, recalculate with marked variables. Okay, so it's only going to do those variables that change significantly in the same direction consistently with the print through. Now look at this. We see we have a much better model. It confirms that we only need 2 factors, so that would answer that question as well. Once we remove those, that third factor was explaining variables that did not influence or did not well predict print through. And we see that much more clear now. And it looks like we have everything is considered significant in our 2 factors. We're explaining 89% of our data. Okay, and now we're using a much more significant portion of our X variability to explain that. And our RMSEs are better. That's great. Now, how do we use this? So once we've built our model, we're happy with this model. What we want to do is test it on a known test set. So I have some in here. Now make sure you go back to your original data, because in the unscrambler, the model actually contains information about any pre-processing you've done, any variable selection that you've done. So you always want to make sure to go back to the original data, because then all of those things will be applied. It's not a big problem if you're doing something like center and scaling, but say you're looking at spectroscopic data and you do a derivative. If you take a first derivative and you take another first derivative, you wind up with a second derivative. So your samples won't predict accurately because the information coming in is not the same as the information that built the model. So just keep that in mind. So we're going to go back to our original data. We're going to predict a regression. We're going to use our final model that we liked. We're going to use process. We want to include the reference, so we want to make sure see how well it's predicting. And we're predicting quality. We're using 2 components because that's what we decided works. Say OK. Oops. I forgot to narrow it down. Hang on. Predicts, regression, PLS2. We want to change this to the test set, so we're only looking at the test set. These are samples that were not included in the calibration at all. These are independent test samples. And this is what we get. It comes up, we get our predicted with deviation. Apparently these don't actually have references, so we can't look at that. But what we see is the red line is the predicted value. In this case, it's predicting at 47. And these are error bars around it. So we would say that this is 47 plus or minus almost 3. What that means is the tighter these are, the more similar the sample is to the original calibration data set. The wider it is, the less confident we are in that information. So you just have to be aware of that. But these all look pretty good. And we can do our predicted versus reference, but it did not come through because we don't actually have reference. Let me show you real quick how you could do that. I'm just going to take a quick selection here. Predict, regression. Now remember, these are not a true test set because they were used in the calibration set, but we can just take a quick look at what it looks like. Okay, so these are our responses. And if we right-click prediction versus reference, we can look at how accurately it predicts. It looks a little messy, but what you really care about here is your RMSCP. So your RMSE is like 2.65. That's a little overly optimistic because these were in the calibration data set, but you want this RMSCP to be close to your RMSE from your calibration data set. And that's how you can tell how accurately it's predicting. I think these look bad just because it's zoomed so in. Right, so they're all fairly accurately predicting. Okay, let me go back to my slides. So, some advice. Make sure you know what question you are trying to answer and why. So you need to make sure to prepare a workflow and figure out what your objective is. Don't look for correlations in your data by plotting endless columns of data. Don't mix your significance with relevance or prediction. And this goes back to how to choose your number of variables. Anyone can fit a model to the data 100%. The correct validation for the problem is the proof of the pudding, right? By definition, your errors, at least in calibration, will tend towards zero the more principal components you put in. You have to make sure to stop when it still makes sense, okay? And it still predicts in the future. There's nothing wrong with concluding that for a specific case, there is not a valid model. I can't emphasize this enough. People expect that there's always an answer. There is not always an answer. Sometimes you have issues with your process data. Sometimes you have issues with your quality that you're trying to predict. It could be that the particular variables that you're measuring don't have anything to do with your output. Say, for example, oh, every time it rains, it happens that I wear a pink shirt. But just because I wear a pink shirt doesn't mean that it will rain. Okay, so keep that in mind when you're building your models. So again, what is a valid model? It depends on your field. It depends on your particular application, right? So if you're looking at computer science or consumer science, that's dealing with people and how they think about things. They're much more flexible in what they consider a good model. Process modeling, like we were just doing, 65%, so your R of about 80, so anything over 65% is actually pretty good. Analytical chemistry, you're looking at 99% or more. Okay? You have to validate your models to confirm your hypothesis. Make sure to do your internal validation. That's going to be your cross-validation and your test set validation. And remember that your models are not a stagnant thing. They are a living entity. You need to revalidate by repeating studies over a year, a couple of months, maybe multiple years, depending on how steady your process is. And if there's any new factors that come in, that can throw off your model. So sometimes you have to bring in new data to update your model to handle new stuff that comes in. All right. So when you're collecting data, a lot of the times we wind up with this historical data. You're given a new project. They say, here's all the measurements we've taken before. Make sense of it. You can do that, but it's the least efficient way to go about it, right? You can just collect data from your process. That's kind of similar to that, but at least you know a little bit more what's going on time. You can perform experiments. You have some idea of like changing the humidity might affect things, so you change things like that. Or you can make designed experiments, and that's a topic of another webinar in general. So the preference is to make these designed experiments to really understand your whole system, but you can make good models from any of these, just so you're aware. This is your workflow. You're going to collect your data, that's your sampling, your acquisition. Make sure to check your data. You can find some strange outliers, like a sample's out of place, or a particular valve wasn't working, so you're getting the wrong temperature, things like that. So just make sure to check your data. You build a model, then you apply that model to new samples, or you check the model by testing it with the test set, then you apply it to new samples. You have some statistical validation for how accurate you think those results are, and then you can move forward. And these are the different steps along the way. Your design of experiments is the best way to collect your data. Your principal components analysis, build your calibration. This is going to be your regression model. Validate it, validate, validate. Don't forget to validate. And then your final prediction. And I'm going to stop there, actually, and I will quickly leave these up for you to look at later if you would like, but I will answer other questions as we go. What sort of error does the offset represent? So the offset only has to do with whether your line goes through 0. And it doesn't really matter if it goes through 0. So there may not be, for example, in this paper example, there may be no paper that has absolutely 0 bleed through, right? That's all that means. Offset and slope. So the slope is showing you how close to a 1-to-1 is, right? So in this case, you're looking at the predicted versus reference, that you want it to be, you want the slope to be as close to 1 as possible. But if your error is low, then you're fine. You know, those are like the last two things I really look at. I tend to look at your RMSEs and your R squared. Those tend to be the biggest values that are the most important. Any other questions? In spectroscopy, does offset give an idea about constant error? Not necessarily, right? Again, your offset is just where that line crosses 0 in the X space, right? So the offset is just so you need your offset and your slope to do your predictions, right? It's just like when you do a traditional univariate prediction where you do y equals mx plus b. Sometimes that b has real meaning. It's sort of like your limit of detection, okay? Now remember, practice makes perfect. So just keep working at it, keep going through it. And if you have any questions after this, please feel free to email me at hbrook with an E at camo.com. And thanks everyone for attending today. Hope you have a great day.